Media, intensity, and loudness. Here are your priming questions. Remember to answer these. Sound travels at different speeds through different mediums, and like the equation that we left off on the previous video, even through the same medium, depending on the conditions, it can be a different velocity. So there are going to be very different velocities between gases, liquids, and solids in terms of the speed of sound through that medium. So for example, even with different liquids between freshwater and saltwater, you'll notice that there's a difference in the velocity of sound. And then comparing that to a solid, for a piece of steel, sound travels much faster through steel than it does through water, and then it's much faster through water than it is through air. When what you want to answer for this question is, why do you think there are those differences? What accounts for those differences between gases, liquids, and solids, and why would that have an impact on the speed? Now, there are other factors other than just gas, liquid, or solid, and these other three also influence the speed of sound through a particular material. And so we have temperature, we have density, and we have elasticity. Typically, as you increase the temperature, like in the equation before for the speed of sound through air, as you increase the temperature, the speed of sound also increases. For density, typically as you increase the density, and this is going to be a hint for the previous question, but you want to go deeper than just density for that. As you increase the density, typically your speed is going to be faster. And again, you want to think about the why. Think about what it is about the type of wave that sound is that would allow density to influence the speed of the wave. The last one that isn't as intuitive is elasticity. And you want to be careful with the way you understand elasticity. This is not stretchability. Stretchability just refers to how much you can deform something. Elasticity refers to how well that material is able to return to its original shape after being deformed or distorted. If it can return easily, it is highly elastic. There are many materials that we wouldn't think of as stretchable necessarily, but are highly elastic. Many metals are actually highly elastic in this regard, and we're going to go through some examples in class. The four listed here are just a few of the examples for the applications. As a quick one, ultrasound. If you've ever seen an ultrasound like this, this is an easy way to see inside of an object without being invasive, cutting into it, and it doesn't damage any of the tissue, anything like that. Sonar, which was developed for submarines and ships to see things in water. This can also be used through the air to see how far an airplane is, something along those lines. Searching for oil, it used to be that you would have to do discovery wells, and you just have to guess at where you think oil is. But using sound waves, you can have a limited blast on the surface, and depending on how those waves reflect and refract through the ground, you can figure out what the different layers are, what material you have, whether or not you have oil there, and you can be much more accurate with drilling for oil. And also, if you've done any competitive fishing or done any sort of fishing on the water, a lot of times you might use one of these, similar to a sonar device, to detect where the fish are, how deep they are, and even the rock bed to see how deep it is to make sure you don't hit the boat on the ground or the floor of the water. Now, sound level. The intensity refers to the exact amount of power that reaches your ear per unit of area. So the units here are going to be watts per meter squared. And this is an actual value that you can calculate. This is the intensity. Okay? And if you think of a tuning fork, if you hear it, there's a certain amount of that energy that is reaching your ear, and there's a certain amount of power per area squared. Now here are a few derivations for power. Okay? So power is equal to I times A, where I is intensity and A is area. So this is just a rearranging of the previous equation where we said I is equal to P over A, power per meter squared. So we can say P is equal to IA. And what's interesting here is if you think of a sound, so if I were to snap, the sound would radiate out as a sphere, like what you can see here, and the center of that would be the origin of the sound. And as it radiates out, if you're somewhere on the surface, the amount of power that reaches you, you can think of like this. And so this would be the surface area of the sphere for wherever you are times the intensity over there. And so 4 pi r squared I will give you the power there. And then if you think of E as energy, this is just another derivation, what we have here. So the total energy is going to be equal to IA times time. And this is just a derivation from power. So these are three seemingly different equations, but they're really the exact same equation. And so when you look at these equations, I want you to think about what that relationship is between the intensity and the distance away. And as a quick reminder here, the radius here is going to be the distance from the center of the sphere. That's going to be the distance to wherever you are from that sound. And the way to look at it, if you have a speaker, the sound will radiate out, very similar to that section of a sphere. For loudness, loudness and intensity are related, but they are different. Your perception of loudness is due to the intensity, but it is not directly related to the intensity itself. It is also related to the pitch and to the tone of the sound in itself. We use the decibel scale to help us understand the relationship between intensity and loudness, so you want to be careful with how we understand it. First, let's start with the equation itself. Beta, which is going to be either the absolute value for decibels or the difference in decibels between two intensities. Beta is equal to 10 log of I over I naught. So these here are your intensities, and I naught is your reference intensity, and we'll talk a little bit more about that in just a little bit. And then I is what you're comparing that to. Now, this is a log scale. Intensity itself is logarithmic with our decimal scale. So for a 10 to 20 decibel, so a 10 decibel difference means that you've increased the intensity by 10 times. So a decibel change of 10 is equal to a 10x increase in intensity. A 20 decibel increase, so 10 to 30, these are all multipliers. So rather than it being another 10x, it's actually going to be 100x. So it's 10 times 10. So a 20 decibel difference means that you are increasing the intensity by 100 times. The thing is about our hearing and our loudness perception, our hearing is logarithmic. And by that I mean, if we have a decibel change of 10 to 20, so a decibel difference, we only perceive that to be twice as loud. The actual intensity difference is 10 times, and this is why we use the decibel scale. Intensity increases by 10 times, but we perceive it to have only increased by 2, so it's only doubled to our hearing. A 10 to 30 decibel increase, so this would be a change of 20 decibels, we perceive to be 4 times louder. In actuality, for the amount of power that reaches our ear per unit of area, that power has increased by 100 times. This is also why it's very dangerous to listen to music at a really loud level, because if something sounds 4 or 6 or 8 times louder to you, that could be well over 100 times the intensity of actual power that's reaching your ear. When working with the equation, the I naught is typically going to be your reference intensity level, and if you're looking for the absolute decibel value, you're going to be using the threshold of hearing, so 1 times 10 to the negative 12th watts per meter squared. So this is if we're looking for the absolute value for the decibels. We can also use the beta equation, the same equation, to tell us our change in decibels as well. And in that case, your I naught is not necessarily going to be your threshold of hearing. It is going to be whatever you are comparing a different intensity to see how much louder something is or how much softer it is, and the decibel difference between the two. And so there are many ways that you can use your beta equation, either to find the absolute decibel value or to find the change in decibels. And so here are some common decibel levels that you can see, and it goes from 0, and we stop at 160 because when you get to 160 decibels, this is when it's actually enough pressure to perforate your eardrum. And so if you ever go to a concert, or if you've ever had a sound that was really painful, that's going to be around 130 decibels, and at that point you have a lot of power reaching your ear. Here are the practice problems that you want to work on. We're going to go through these in class. You need to attempt these. you can pause so you can write them down and work on them. And then here are your priming questions again. Please remember to write these down.